It's time. You have survived. It is time for the final video lesson of the summer. There's probably like 3,000 more of these coming over the school year, but let's do it. So we're going to switch gears. We're going to do some more math. Today we're going to work with some two-way tables. That was a weird noise. But let's do that so we can wrap this thing up, huh? So working with some categorical data, some two-way tables. If you took geometry and stat at our school last year, this is definitely something that you've had some exposure to at least. All right. So a two-way table or a contingency table, some notes here, right? So a two-way table, a contingency table shows us counts based on two categorical variables. And we can use these tables to investigate if there's a relationship or an association between two categorical variables. So actually in the very this is a question, is there a relationship between two categorical variables? We'll kind of address this now a little bit informally. When we get into the probability unit, we'll look at the independence formula to address this question. And then when we get into statistical inference, like in April, maybe we'll learn about chi-squared and do what's called a hypothesis test. So this is a kind of a question that we're going to continually revisit throughout the year. And just some vocab here, right? Another way I could ask is I could say, is getting a ticket independent from age group, right? So independent means no association, no relationship. Not independent means there is an association or there is a relationship. And so here's just a sample of these two-way tables showing us two categorical variables. First categorical variable is did you get a ticket or not? Second categorical variable is age. Age is one of those variables that can be used either way. So we could use age quantitatively as a measure of how long you've been alive. Or here we're just using age to put people into groups. So here age isn't used quantitatively, it's just used to put you into one of these three categories. So we've got two variables, age and then ticket or not, and we're looking at the counts or numbers of people that fell into each. And so this is called a two-way table, right? Got variables going two ways, or a contingency table because it's showing the distribution of one variable, one categorical variable, contingent upon another. Side note, all SAT probability is based on two-way tables. So we'll have a full probability unit where we get into some more complex stuff, a lot more complex stuff, right? All SAT probability is based on these. A two-way table doesn't have to show just numbers of people or things in each cell, in each, or each box or whatever, right? A two-way table can also show probability. So we look here, this is a 2019 AP Stat Free Response question, and this, right, shows I guess a person's gender and then their response to some question, right? But here we're not seeing the number of people, we're looking at the percent or probability for each, right? So just to be aware that can happen. All right, so here's our context, and we're just going to start working through some questions, and then that's it. So insurance companies conducting a study in Connecticut of at-risk drivers. At-risk is defined as people who are most likely to be in an accident. So the insurance company decides to define each of the following groups as at risk: if you're under 21, over 75, or if you have a ticket in the past year. So the insurance company takes a random sample of 1,000 Connecticut drivers to determine their age and whether they've gotten a ticket in the last year. So here we go. We're just going to work through some questions. So if you're taking notes, you might draw this table at the top, and then you might just write like A. A way to shorthand this is P parentheses. That means what's the probability that you could say like random driver is over 75. All right, so that's just kind of a way you can shorthand this. So when we look at this, we're just talking about any randomly selected driver. So each of these we're going to want to show a fraction, and then we're going to want to show a percentage or probability. To determine the denominator, we want to kind of focus on the wording here. So we're talking about any randomly selected driver. We don't know if they're over 75, under 75. We don't know if they got a ticket or not. We're just talking out of any driver. So our denominator here, we're talking about out of all 1,000 people. And of all those randomly selected drivers of all 1,000, we want to know what proportion of them were over 75. And we have a total here that I've covered up of 95 people over 75. So 95 of the 1,000 people were over 75, and 95 over 1,000 gives us 0.095. And so we're going to show a fraction and our probability. Typically, probabilities are written as a number between 0 and 1, so a decimal. If you wrote this as 9.5%, you know, it's not going to bother me that much. So there we go. Question 1. Done. Time for the next one. All right, B. So now we're looking at what's the probability that a driver who did not receive a ticket in the past year is between 21 and 75. So here we have a little bit of a different situation, because here we know we're talking about a driver who did not receive a ticket in the past year. This is what we're going to call conditional probability. We're given some information. We're given something, some condition that has to be met. It has to be true that the driver did not receive a ticket in the past year. So we don't care about any of these people who got a ticket. We only care about all these drivers who did not get a ticket in the past year. So for me, oftentimes it's helpful to write on these tables. So out of all 747 who did not receive a ticket in the past year, we want to know just of these people, how many of them were then between 21 and 75. Well, of the 747 that didn't get a ticket last year, 634 of them were between 21 and 75, and 634 divided by 747 gives us 0.849 or 84.9%. So this is conditional probability because we know something, right? We know they didn't get a ticket. One, I would write this if I were using my notation. Big P means what is the probability? So I would say, what's the probability someone is between 21 and 75 given? So this symbol right here, this slash, this is not divided by. This means given we know that the person did not get a ticket in the past year. So what I've just written in black here, that's the same thing as the question that's in a sentence. What's the probability someone's between 21 and 75, given we know they did not get a ticket in the past year? So not only are we doing a little bit of math here in the purple box, but also we've got some new probability notation to consider. All right. Moving on, let's see what we got next. So it's all about reading carefully as you're looking for some of these on your summer assignment. So C, what's the probability a randomly selected driver is over 75 and received a ticket in the past year? So here, now we need somebody who's over 75 and got a ticket in the past year. So first off, how many people meet that criteria, are over 75 and got a ticket in the past year? That refers to these 11 people right here, right? These 11 people are the only people who are over 75 and got a ticket last year. For the denominator, again, we're talking about any randomly selected driver. Now, some students want to think that when they see the word randomly, that means the total. That's not really true. I can use the word randomly in any question. But the key is here, we're just talking about any driver, right? What's the probability that a driver, right? It doesn't matter if they got a ticket or not. It doesn't matter if they're over 75, right? We're looking out of any driver. So we're looking out of all 1,000. And so we're going to get 0.011 for that one. So an and probability, while we're given two criteria and kind of to see where those meet. All right, not so bad, right? This is all stuff that you guys did in geostats last year if you took it. I know that, you know, because I taught it. But anyways, how about D? What's the probability that a randomly selected driver is over 75 or got a ticket in the past year? So now we're in a totally different situation. So again, we do have a randomly selected driver. We're looking out of any driver, right? So, whoops, for our denominator, pretend that didn't happen, right? For our denominator, we're talking about any driver right here, and there are 1,000 of them. So we want to know what's the probability they got a ticket or were over 75. Well, over 75, there's 95 of those people. So we had 95 people over 75, plus we've also got 253 people who received a ticket. So this gives us 348 out of 1,000, or 0.348, which I will tell you is the most common incorrect answer. I told you I like to do that. Hopefully, as I was writing that, you were like, I don't know, man. I don't know if that seems right. What's the mistake here? 0.348 is too big, is too high. What mistake did we make by adding these two totals for the total probability or the overall probability that someone received a ticket or was over 75? As you're looking, even if you look at the way I wrote on the table, hopefully you realize these 11 people got counted twice, right? These 11 people got counted in the traffic ticket group, but they were also counted in the over 75 group. Like if I'm looking at the total number of students who take AP Stats and AP Calc, if I just take my total number of students and Ms. Bergeron's total number of students and add them, that's going to be an overestimate because that counts all of the students, all of you guys who take both of our classes, you're getting counted twice, right? You're getting counted with Ms. Bergeron's list and with my list. So to account for that, we now have to subtract 11, the 11 people who got counted twice, so we have 337 out of 1,000. Or 0.337. So here, we're talking about probabilities. The formal language would be we're talking about probabilities with events that are not disjoint. Probabilities with events that have overlap. Or more generally, anytime you have one of these or questions, you always want to make sure you look for overlap and make sure you don't count anyone twice. Now, another way to approach this, I could, ignoring the totals, I could just go through my table here, and out of the 1,000 people, kind of think, were they over 75 or did they get a ticket? So like these people, were they over 75 or did they get a ticket? Yes, they got a ticket. Were these people over 75 or did they get a ticket? Yes, they did both. Like, do I have a shirt or a headband on right now? You're gonna be like, oh, you have both. But like, no, it's a yes or no question. Yes, I do, because I have both. So these people, yes. Were these people over 75 or did they get a ticket? Yes, they got a ticket. Were these people over 75 or did they get a ticket? No, they don't fall in either group. These people, yes, they're over 75. And then these people, no, they're not over 75, nor did they receive a ticket. So another way to approach this would be to just kind of ignore the totals and go through each cell on the table and think, do they satisfy over 75 or got a ticket? And if I now add these four numbers from the table with the check marks next to them, I'm going to get the same answer. I'm just going to double check. Like, I'm pretty sure I know what I'm doing, because I taught stats like 12 times, but why not double check? It works. So that gives us 337 out of 1,000 or 0.337. You do what works for you. But if you're going to add the totals, make sure you subtract any overlap. So this is going to connect, and when we get to some more formal probability, we'll talk about something called the general addition rule. But for now, just know how to do two-way tables and ace your SATs and stuff if they happen. Who knows what's happening, what's going on in the world. Anyways, all right, question E. What's the probability that any driver received a traffic ticket in the past year? I just put this on here to try to get rid of the word randomly, right? Any driver means we're talking out of 1,000, right? So no big deal. Any driver, boom. Out of all 1,000, how many got a ticket in the past year? 253. How about F? I didn't explicitly say that, like, you should pause these and try them yourself, and I'm kind of far into it to do that now, but, like, I really hope you've been doing that. So, like, do this one. It's probability that a given driver who is under 21. So here we have more of that conditional probability. So a given driver who is under 21. We know we only care about drivers who are under 21. So we don't care about these people. We don't care about these people. We only care about the drivers who are under 21. So we only care about 53 as our total. I'm going to write this with that other notation. We want to say, given someone is under 21, what's the probability they received a traffic ticket? Of these 53 drivers who are under 21, 24 of them received a traffic ticket, right? These 24 out of 53. I think that's like 0.453, yep. And so that gives us 0.453. So we got more conditional probability, right? We know something about that driver. We know that they are under 21. All right, almost done here. So to finish up with this table, let's look at question G. So some writing here. So question G asks, based on your answers to E and F, so the questions we just answered, do we think that receiving a traffic ticket and age are independent? And we have to explain our reasoning. Remember, independent means not related. So do we think these are not related or related? Up here, we know the probability that any random person gets a ticket is about 25%. So if any random car drives by me, and I don't know anything about that person, there's a 25% chance they're going to get a ticket. Here, this is the probability someone gets a ticket given I know they're under 21. So if any random car drives by me and I don't know anything about them, there's about a 25% chance they get a ticket. But if a car drives by me and I know the driver's under 21, that now tells me there's a 45% chance that they were going to get a ticket. So the question is, did the age seem to impact the chances we get a ticket? If it did, it means age is related to getting a ticket, and these things are not independent. If age doesn't really seem to impact the chances you get a ticket, then that would suggest that age is not related to getting a ticket and that these things are independent. Hopefully, as we look at these numbers, we can all agree it seems like if you're under 21, you are more likely to get a ticket than some random driver. Right, so that's going to be our reasoning, right? The reasoning here is going to be if a driver is under 21, then he or she is more likely, right, about a 45% chance to get a ticket than a random driver, which is about 25%. That's our reasoning. What does that tell us? Well, that tells us your age matters. That tells us if you're young, you're more likely to get a ticket, which means receiving a traffic ticket and age are related, or in other words, are not independent. Now, one general strategy I'm going to give here, when we're writing on the AP exam, one of the best things you could do is just reword the question. Then you'll never mess up your context. So to start, I would say receiving a traffic ticket and age are, now we want to answer the question, are not independent, right? Not independent means they are related, because if a driver's under 21, they're more likely to get a ticket than some random driver. What I've written in pink and green is a essentially correct response on the exam. That's perfect. It's okay. We use the arrow and stuff. I'm not necessarily grading your structure. Of course, it's got to be, clear. It's got to be concise. It's got to be thoughtfully written, not a bunch of random, bullets here and there. But we've answered the question in pink directly, right? We're saying receiving a ticket and age are not independent. They are related. We're answering in context, and then we're explaining our reasoning. So we want to compare these numbers. If these were about the same, then it would seem like age wouldn't really matter, right? Like if you were under 21, that gave you a 27% chance of getting a ticket. All right, that's like pretty close. So like being under 21 doesn't really change your chances of getting a ticket. So then we might say those things are independent or are not related. I don't have an answer for you as to how far apart those numbers have to be. That's what's called statistically significant. That's coming later in the year. But generally speaking, if the 2% are about the same, roughly the same, then the two variables are not independent, are not related, are independent. But I would think less about that kind of formulaic approach and more kind of realistically here, right? In blue, if you're under 21, you got a higher chance of getting a ticket than any random driver, all right? And really, we're using what's called the independence formula here. We're just using it a little bit informally. That question G typically is one of the hardest questions in the first unit. So if you're looking at that and you're struggling, you're challenged, you're whatever, like that's normal. When I give the first unit test, this is usually for many students one of the tougher questions, because not only do we have to understand how to approach it, but it has to be well written. All right, let's see here. Let's clear this out. And so to finish up, I challenge you to work with a slightly different context and try parts A and B of the 2019 free response. Part C is some more kind of advanced probability. Part A here, though, these are very similar to some of the things we addressed right now. The only difference is this is given in terms of probabilities already. And then part B, you can see, right, is another one of these independent things that we just kind of touched on. After you try those, I would try to look at the answers. So anytime we have a free response, and a lot of times in class or in our distance learning, you're gonna have to score your own response. So if you just Googled this, right, you can see I just Googled it right there, the scoring guidelines, the third thing down, not the purple one. And when you get to the rubric, you would scroll down to the question. It's gonna show a solution, right? So do this, but then, right? Those are the answers. And then it's, oftentimes students wanna just look at the answer and see if they match. But for us to do well in this class, we need to understand how the exam is scored. So to me, more important than the solution is reading through the scoring. So again, these are scored as essentially, partially, or incorrect. It's not all points. So read, like, what do I need to do to get essentially correct? No one in here, we're not aiming for partially and incorrect. Partially is a solid score, but we're all striving to get that E on every single thing we do. And then read these notes. Those are important. The more effort you put into, and then here's part B, the more effort you put into reading these rubrics, the more insight you'll have into how the exam is scored. And I score everything in class the same way the exam is scored. So you'll also know what kinds of things that I'm looking for when I'm, reading over your responses. So that's it. So we're gonna have a quiz when we come back to school. It's gonna be within the first few days. We'll figure it out. This is what's on it. This shouldn't be a surprise. Each bullet is pretty much a video. So intro vocab was lesson 1 video. Creating histograms was actually lesson 3. Reading histograms was lesson 2. Calculating summary stats, came up with the box plots in lesson 4. Creating a box plot, lesson 4. Comparing reading box plots, we kind of skipped over that. I'm not worried about that, so don't worry about this. Finding mean of combined samples, we just did that in lesson 5, and this is what just happened now. So yeah, I'm that guy who's going to give you a quiz early. All right, looks like that's a wrap. I hope to see you guys in some office hours, but you don't have to wait till then. If you're watching these and you have questions, don't hesitate to send them in Remind. I was going to say I can't wait to get to work, but like we've gotten to work, and I appreciate it. I appreciate you guys. I can't wait to meet you soon. Peace.